Thank you. And it barely seems like 5 minutes I was last here talking to you. So, now for the serious part of the evening, having covered that. The science of Santa. How many laws of physics does Santa break, apparently? Well, Santa is allegedly a portly, jolly fellow with a white beard and a penchant for wearing red suits. But just because he's got questionable fashion sense, that doesn't necessarily mean he doesn't exist. So the question is, what about the claims made about this gentleman? He allegedly visits all households on Christmas Eve to deliver presents to qualifying children. And qualifying can be taken different ways, but one way is to think about the naughty nice list. Can we reconcile that in terms of what science we understand about how the universe works? And I thought to deliver this particular talk, I would draw on talks that I've given, not necessarily to this society, but more generally. In other words, from what we know about other aspects of how the universe works, what can we say about Santa? So again, let's just place it there and remind ourselves that this is what we are addressing this evening. Santa visits households on Christmas Eve to deliver presents to children. We're going to take that phrase and unpick it essentially one word at a time. Firstly, children. How many children does he deliver presents to? Well, roughly speaking, the world population is 8 billion, 25% are children, according to the latest statistics. Let's assume half of them are eligible for Christmas presents. I know they're not necessarily Christian families, but Santa is a nice man. He will deliver presents even if the families are not Christian. So that means Santa has got to deliver presents to about 1 billion children. Again, that's subject to naughty nice. Let's assume naughty is 0 and nice is 100. Most parents would quibble with that ratio, but let's just keep it simple. Okay, so we've got 1 billion children to take care of. Santa apparently visits all of these households. How does he get around? What's his mode of transport? Well, he's got a sleigh, and the sleigh is pulled by flying reindeer. So question 1, can reindeer actually fly? Well, we know insects can fly, and we know birds can fly, and we know pterosaurs can fly, though you don't tend to see that many of them these days. And we know that mammals can fly, or some mammals can fly. So if mammals can fly, why not reindeer? Well, if they can fly, they choose not to do so for a lot of the time, because we've never actually caught one in the process of flying. So there's very little evidence for flying reindeer. But remember, as scientists, you must always admit that absence of evidence is not the same as evidence of absence. So just because we haven't got any images or videos of reindeer flying doesn't mean they can't. So the jury is still out on that one. Okay, how fast would he have to travel if he wanted to deliver presents to everybody on Christmas Eve? Well, to visit 1 billion children, let's say it's over 36 hours. He's got Christmas Eve night, and let's assume he uses the time zones sensibly. That gives him about 36 hours. And it depends on how they're distributed around the world, because of course population centers are not uniform around the world, but you can do a rough calculation and you figure that he would have to travel at a minimum of 0.007 times the speed of light. That's a tiny fraction. That's not even 1%. He could go 10 times that fast, and he would only be going at 7% of the speed of light. Nowhere near fast enough to break any rules of physics. So we know that no object can travel through space faster than light can travel through a vacuum. Now we know that space is expanding, the universe is expanding, so space can expand faster than light, but no object can travel through space faster than light. But Santa isn't even close to breaking that speed limit, so he's fine as far as that is concerned. But if he's going really, really fast around the world, won't we have roast reindeer? Surely, moving that fast, things are going to get hot, just like a meteor or an asteroid coming into the Earth's atmosphere. It's not friction that matters. What happens is that the air in front of the object gets compressed and heated up. So if it gets really hot, surely it'll be glowing white hot. So we know that compressing things makes them hot. That's the C of the ABC of stellar evolution. I gave you this talk many, many years ago. And the C of the ABC stands for compression produces heat. So if Santa is going around the world really fast, the air in front of the sleigh should be compressed, and we should end up with a very white-hot sleigh and a lot of roast reindeer. Okay, so what's the way around that? Even with an aerodynamic sleigh, that's not really going to help that much. Shouldn't there be a really bright light in the sky? If he really is going that fast, he's going to get really hot. Shouldn't there be a really bright point of light in the sky? Well, yeah, maybe there was. But yeah, it's pushing it a bit to claim that Santa is actually the Star of Bethlehem. The timeline doesn't quite work out right. But you could say, well, maybe it wasn't the Star of Bethlehem, but if you're trying to explain bright lights in the sky, well, yeah, there's plenty of people who claim to see bright lights in the sky all the time. So, yeah, maybe the sleigh is visible when he decides to go that fast. But there's an alternative. There's lots of alternatives in this particular talk. You could say that if he moves really fast, he's going to get hot. If he gets hot, he's going to glow like a supernova. Well, not all matter behaves that way. What matter do we know about that even if you heat it up, doesn't radiate light? Well, we all know what that is. Dark matter doesn't radiate light. Doesn't matter how hot you get it, it will not radiate light. Dark matter doesn't absorb light. Dark matter doesn't radiate light. So if Santa and his sleigh are made of dark matter, everything is hunky-dory, because you wouldn't expect him to glow like a supernova as he goes flashing over the sky. And also, by the way, that explains why he doesn't show up on radar, because again, he doesn't absorb. If you don't absorb electromagnetic waves, then you don't absorb or reflect radar, so he doesn't show up on any radar. Okay, so everything is nicely consistent so far. Let's examine the next bit. He visits lots of households. Not necessarily 1 billion, because of course there's usually more than one child per household. So, how does he get down the chimney? He's regardless of portly, he's a portly fellow with a girth which would imply that he's not going to be able to get down chimneys, especially if he has to go down 3,000 chimneys a second. That's asking a lot of somebody with a fair old girth. So how can he possibly do that? Surely it's impossible for an adult male to go down a chimney, especially fast. Well, true, if he's made out of the same stuff as the rest of us. But we know from quantum theory that atoms are made of nuclei and electrons have cousins called muons. They're like electrons, but they're just 200 times heavier. So what if Santa could somehow replace all of his electrons with muons? Then all of his atoms would be 200 times smaller, which means instead of being a gentleman a little less than 2 meters high, he would be about 1 centimeter high. And he would slip down chimneys no problem whatsoever. Now, how you go about replacing every electron in your body with muons, I don't quite know, but there's nothing in the laws of physics that stop you doing that. And there's nothing in laws of physics that stop you being 1 centimeter tall if you're made of atoms with muons rather than electrons. Okay, but that doesn't help if you haven't got a chimney. What if you've got a house or apartment without a chimney? How is Santa going to get inside? Well, quantum theory comes to our aid once more, because it's possible to go from inside a building to outside, or from outside to inside, without going through an open door, without going through an open window. It's a quantum process called tunneling, whereby, according to Newton, it should be impossible to go outside to inside, because otherwise you'd have to pass through a solid wall. But in quantum theory, there's no problem with that. In other words, it is possible to tunnel through, as the expression goes, from outside to inside, even though there are no doors open, no cracks in the bricks, no windows, no chimneys, etc. So quantum theory comes to our rescue once more, and it's perfectly allowable by the laws of physics to pass into a house without going through a chimney or an open door. Okay, so he's visiting households. He's doing all of this on Christmas Eve. So he's only got 36 hours or so to do this, all in one night. How can he make so many deliveries all in one night? Even traveling at relativistic speeds to all of the various delivery houses, how can everything be done in 36 hours? Well, quantum theory, yet again. Quantum theory says that subatomic particles can be in 2 places at once. An electron can be here and there at the same time. It doesn't meet with our common sense, but that's because our common sense is wrong. Quantum theory, as far as we know, is correct. And if quantum theory says it's possible for a particle to be in two places at once, why can't Santa be in two places at once? Or three, or four, or 10,000? He can be in as many places as he wants according to quantum theory. That is not disallowed by the laws of physics. But there is another alternative. If you don't like that idea of Santa being in multiple places at the same time, even if you want to restrict Santa to being in only one place at a time, then there are alternative ways of getting over vast distances around the Earth. And that is, you don't leave these vast distances as vast distances. You actually distort space so that all the houses come to you, rather than you have to travel to all of the houses. We know that matter distorts space and distorts time. That's part of Einstein's general relativity. We tend to think of it in terms of black holes, but in principle, any matter will distort space and distort time. So you can think of it as either warping space or distorting space or folding space if you prefer. So if Santa was capable of distorting or warping or manipulating space and time, then he could bring all of the houses to him to deliver all of these presents in only 36 hours. So we've done visiting households, Christmas Eve. He's got to deliver a lot of presents. We've talked about 1 billion children. Let's assume they get a present each. Let's not be too mean about this. So if they're all getting a present, that means 1 billion children. How can the sleigh possibly hold 1 billion presents? It's not big enough. If it's big enough to actually be pulled by reindeer, then surely it's not big enough to hold 1 billion presents. Well, it can if it's bigger on the inside than the outside. And for those thinking of a TARDIS, no, that's not what we're thinking of. We're not thinking of science fiction. We're talking about science fact here, science fact. Black holes are bigger on the inside than they are on the outside. It is possible to warp space in such a way that the volume of a container is bigger than the outside would have you believe. In other words, you can have a sphere or a sleigh which is bigger on the inside than it is on the outside. That is allowed according to Einstein's general relativity. So, great, we can do that. Alternatively, if you don't like that idea, there are other options. For instance, all you have to do is to store all the presents in another dimension. Now, we think there are 3 dimensions, forward, backward, left, right, up, down. But a lot of people, especially physics theorists, believe there are actually more than 3 dimensions, but we're only aware of 3 of them. Maybe there are 10 or 11 or more dimensions, in which case maybe Santa somehow has access to these dimensions, in which case he just pushes all of the presents into one of these other dimensions, flies around, gets to a house, and then pulls the presents out of that dimension back into our dimensions and puts them under the tree. Again, we can't prove or disprove the existence of these other dimensions, but there's nothing in the laws of physics that say they can't exist. So maybe Santa has figured this out somehow. Okay. But you might say, this is ridiculous, because everything you're saying would need a huge amount of energy. If he's going to go really fast and if he's going to distort space, etc., surely you can only do this if you have humongous amounts of energy to play with. True, yes. A Santa and a sleigh and 1 billion presents moving at relativistic speed would indeed need a huge amount of energy. But all you need is a black hole to power, for instance, if it can power a starship, then surely a black hole can power a sleigh. And yes, the amount of radiation that you get from a black hole from just outside the event horizon, that radiation could be enough to power a starship to the stars. We haven't figured out the technology of how to build one, but the physics is sound. So if you can use a black hole to power a starship, why can't you use a black hole to power a sleigh? Wouldn't that give you enough power? Well, it would certainly give you a fair bit of energy to play with. Would it be enough for the circumstances? Well, maybe, maybe not. But there's an energy source that we're overlooking. Rather than invent something ridiculous like black holes, there's an energy source that we're missing that Santa could be tapping into. The elephant in the room, the thing I haven't mentioned yet. What happens to all the mince pies? Lots of people put mince pies out for Santa. Now, no one is silly enough to think he eats them all. Surely, come on. Millions of mince pies in one night? I don't think so. I know he's portly, but he's not that portly. So what happens to all the mince pies? Well, if Santa could convert the mass of all the mince pies into energy, then he would have E equals mc squared to play with. We know E equals mc squared is, if you like, the sort of exchange rate between, for a given amount of mass, how much energy, in principle, could you release from that mass? E equals mc squared. So we can do a little calculation. For those that don't like maths, look away now, because we're going to do some. A mince pie is about 50 grams. So 50 gram mass multiplied by the speed of light squared gives you an energy of 5 times 10 to the 15 joules. Now, I know you don't like joules because that's an energy unit that physicists use. You might prefer calories, but it's essentially the same number in calories. We'll deal with how big a number that is shortly. But that's one mince pie. How many mince pies has Santa got? Well, we don't know how many people leave out mince pies. Let's assume it's just a few percent of all the households leave Santa the mince pies. And let's not worry about the carrots for Rudolph. So a few percent of households multiplied by all the households. Let's say 20 million mince pies are left for Santa. 20 million times 5 times 10 to the 15 joules is 10 to the power 23 joules. And I know that means nothing to you, so let me give you that in units you might understand. That amount of energy, which in principle is available to Santa in one night, is equivalent to a nuclear power station running for 1 million years. Or if you like, during the night, it's equivalent to Santa having 1 billion power stations at his beck and call. Loads of energy, more than enough to travel at relativistic speeds with 1 billion presents. Easy. How do you go about extracting E equals mc squared from a mince pie? We agree that it's 50 grams of mass. We agree there's a lot of energy in there. How do you get that energy out of the mince pie? Well, okay, that could be slightly problematic. There's a couple of ways I can think of to do that. One is to take the mince pie, one at a time, and what you take is an anti-mince pie and collide them together in the Large Mince Pie Collider at CERN. Now, okay, that should be doable, but yeah, where do you get the anti-mince pies from? That's the problem. Mince pie antimatter is fiendishly difficult to get hold of. So although in principle that will release all the energy, part of the problem is the right-hand side of that particular diagram. So given that we've got a lot of mince pies, what's a way of releasing the energy without finding an anti-mince pie? Well, there is a way to extract not all, but a reasonable fraction of all the energy in any matter. It's an amazingly efficient process. You can extract maybe 10% or 20% of the energy of a body, not by, for instance, putting it in a star and having it fuse hydrogen into helium. That's very inefficient. Less than 1% of the mass is actually converted to energy in a star. There are ways of converting 10%, 20% of the mass into energy. What do? You drop it into a black hole. Matter falling into a black hole is amazingly efficient at converting matter to energy. It happens, for instance, at the center of galaxies. Some galaxies are quasars. Quasars are galaxies which have a black hole at the center in which a lot of matter is falling in, and that generates so much energy, these quasars can be seen even at fantastic different distances. During COVID, I set myself the challenge of taking an image of one of these quasars at the phenomenal distance of 25 billion light years. This is without a telescope. This is just with a camera. I photographed a quasar at a distance of 25 billion light years. That's such a ridiculously large distance. With the expansion of the universe, this quasar is actually receding from us at twice the speed of light. But so much energy is coming out of this quasar, it can be imaged even without a telescope. So that tells you just how efficient it is to drop matter into a black hole. Now, in the case of a quasar, the matter is probably not mince pies that are going into the quasar. They're probably stars and things like that. And surprisingly enough, I actually can't find much information about how much energy is released when a mince pie falls into a black hole.
Just about your imaging the quasar without the telescope, tell them where you imaged it from as well. It wasn't like a mountaintop telescope.
My front garden behind a wheelie bin. I'll tell you more in the Q&A if you wish. So Yes, quasars probably not eating mince pies. They're probably eating larger amounts of matter. But the point is, matter falling into a black hole is converted to energy via a very efficient process. So maybe Santa has got a little black hole. Maybe it's the same one that's powering the sleigh. And if he drops the mince pies into there, he gets energy out, enormous amounts of energy. So maybe that's how he actually carries out these things. So this is possible, but how could he do all that? All these things I've described are possibilities that are allowed by the laws of physics as we understand them at the moment. But how exactly could Santa manipulate space and time in this way? We don't really understand how. But remember, throughout this, we've made an assumption. We've made an assumption that Santa is a man, but who says he has to be human? Maybe Santa is... Okay, he doesn't have a white beard in this particular rendition, but yeah, no one has seen Santa, remember. All children are asleep when Santa visits, so maybe he does look like that. Who knows? Okay. So, how many laws of physics does Santa break? I would say none. So feel free to draw your own conclusions about the existence of the portly, jolly fellow with a white beard and a penchant for wearing red suits. And of course, regardless of your conclusion, for the second time this evening, I wish you all a very Merry Christmas.